Hello, now we move to the second part of op-amp, which is the model of op-amp and its characteristic. We know that the input impedance is infinity, the output impedance of op-amp is 0, the AO or A open loop for op-amp is also infinity. VD is the difference between non-inverting terminal with respect to the inverting terminals. Okay, we have defined I plus the current entering the op-amp, and I minus is also the current entering the op-amp. Now we look into the infinite voltage gain. Okay, we want to amplify the difference between the non-inverting terminal with the inverting input. Okay, and for op-amp, the gain is determined by the manufacturer, and in practice, usually the open loop gain is more than 100,000. Usually it is between 200,000. Okay, AO is also known as AOL or open loop gain. This is the equation defining the output voltage with respect to the output AO and the difference at the input VD, where VD is V plus, subtract with the V minus. And AO is also we call as AOL or open loop gain of the amplifier, and VD just now we define as the difference between that, V minus at the inverting and V plus is that non-inverting input. Now, if you look at this model of op-amp, due to the input impedance infinity, so we can say this is an open circuit due to the high input impedance. Okay, since the input impedance is very high, we say that there is no current entering op-amp. I plus is 0 at the non-inverting terminal, and similarly at the inverting terminal, I minus is also 0. And for the output impedance, we know that the value, the ideal is 0. Since we said that input impedance is very high, which is infinity, we said that there is no current entering the op-amp. I minus and I plus is equals to 0, and the input terminal is virtually open circuit. As for the output impedance, it is 0. Hence, the output voltage we can write as VO equals to AO VD, which is AO multiplied with V plus subtract with V minus. And using the infinite gain characteristic where AO or A open loop is infinity, we can rewrite the equation just now. V plus subtract with V minus is equals to VO divided by A open loop. Substitute A open loop with infinity. VO divided by infinity is equals to 0. So with this, we can say that V plus is equals to V minus. This is the second important equation for op-amp. And due to this, we can say that the input terminals are virtually short circuit. Okay, you can look over here. Since we say that V plus is equal to V minus, it seems that as if V plus is connected directly to V minus. So this is appear as a short circuit. So with those two, if you look at this particular circuit, we have a circuit like this. Since your V plus is connected to common ground over here, or we call it earth, meaning that the V minus over here, which is we say that equals to V plus, this voltage is also appear as 0. Okay, so this is called the virtual earth. The V minus is not really connected to ground, but since V minus is equal to V plus and V plus is equals to 0, so V minus is equals to 0 as if it is connected to ground. And the next characteristic of op-amp is the bandwidth. We said that the bandwidth of ideal op-amp is infinite, meaning that the gain is constant over a wide range of frequency. But in practice, the bandwidth is limited to a few megahertz. Okay, so what you see is like this. This is the ideal value of your bandwidth. So meaning that your gain is constant throughout the frequency, but in reality, the gain will drop at a certain high frequency. It depends on the manufacturer. And another characteristic of op-amp is a slew rate. Okay, the output of op-amp does not change instantaneously because previously I've shown that Op-amp is actually a multi-stage amplifier. So meaning that when you have an input signal, it has to propagate through several stages of amplifier before you get the output. Okay, so the rate of change output is limited. Okay, for example, if you have an op-amp with a slew rate of 0.5 volt per microsecond, meaning that it will take about 20 microseconds for the output voltage change from 0 to 10 volt. Okay, so what you see is that we have what is called slew rate, which is the measure of rate of your voltage changing with the with respect to time. So it is measured in voltage per second, delta V over delta T over here, how fast your output changes with time. Okay, since op-amp is not ideal, so the signal has to propagate, so there is a slope over here which is called a slew rate. A good op-amp shouldn't have a slew rate, meaning that you shouldn't get this type of output, meaning that whenever you have changes in your input voltages, your output should be automatically a straight point over here. There shouldn't be any slope. Okay, and another characteristic of op-amp is called common mode rejection ratio, or we call it CMRR in short. And the CMRR is a measure of the ability of op-amp to reject a noise actually. And since noise is coming in the form of common mode, okay, CMRR is defined as AD divided by AC, where AD is the differential mode gain and AC is the common mode gain just now, which is the noise. And usually the CMRR is calculated in dB, okay, where CMRR in dB is 20 log of AD over AC. It is 20 log because we measure the AD and AC in terms of voltages. So a good op-amp must have the differential mode gain, which is much larger compared to AC. AC should be as small as possible. Okay, and this is the minimum typical value of op-amp, usually around 70 dB, and the highest around 90 dB. It could reach also more than that. Okay, so just now I mentioned that the common mode gain AC must be as small as possible because it is the noise. Okay, we want to cancel or reject that. Okay, this is an example of datasheet for op-amp. This is for LM741. 741 is actually a general purpose op-amp. So you can have the package in terms of metal can or dual inline. Okay, it could be also ceramic flat pack. Okay, usually we'll have around 8 pins. Okay, this is also 8 pins, but for the ceramic flat we have 10. Okay, so basically the inverting input is at terminal pin 2, non-inverting pin 3. You have power supply V plus V minus, and output is pin 6. We have offset null over here. We'll talk about that later. Pin 8 is no connection. For the 8 pins, so you have pin 10, 9, and pin 1, it is not connected to anything. Okay, so for datasheet, it will give you several inputs or parameter about the op-amp. So I just want to highlight this thing, the input resistance just now, Zi or Ri. If you see over here, it is in 2 mega ohm. So finite, the ideal value is infinity. So we have about 2 mega, which is considered very high. And the output impedance over here 75 ohm. Okay, the ideal should be 0. Okay. And just now I mentioned about the CMRR. So this is the typical value, 70 to 90 dB. Okay, and also in the datasheet example, you have output voltage swing. Usually the voltage swing is, in this case, is plus minus 20 volt, which is actually your power supply, plus minus VCC. So that is the maximum voltage swing that you can get. Okay, and this is the bandwidth. So for this example, your output will reduce at 1.5 megahertz. Okay, and another one is just now slew rate, the measure of your output changes with respect to time. Okay, so this is measured in volt per microsecond. Okay, it is about 0.7. Okay, thank you.